Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI-generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will explain how to schedule jobs on the Fram Linux cluster using the Math Kernel Library, MKL, to perform matrix multiplication. You can find information about the Math Kernel Library on Intel's website. The web page is part of the developer reference for Fortran. MKL is an optimized library by Intel offering a variety of mathematical functions for scientific computing. It includes linear algebra, fast Fourier transforms, vector math, statistics, and data fitting. MKL is designed to maximize the performance of Intel processors through parallelism and vectorization, making it ideal for high-performance computing. As we scroll down the page, we can see the various routines included in the Math Kernel Library. We will use one BLAS routine. BLAS, which stands for Basic Linear Algebra Subprograms, is a specification that prescribes a set of low-level routines for performing common linear algebra operations, such as vector and matrix multiplication. BLAS implementations are optimized for performance on various hardware architectures, making them a fundamental building block in many high-performance computing applications. Let's navigate to the BLAS routines page. BLAS is divided into 3 levels. Level 1 is operations on vectors such as dot products and vector scaling. Level 2 involves matrix vector operations. Level 3 involves matrix-matrix operations. Since we need matrix-matrix operations, we'll look at the BLAS Level 3 routines. Here we select the GEMM routine group, which computes matrix-matrix products with general matrices. After selecting this group of routines, you'll notice there are many different subroutines available. We will use the DGEMM subroutine. This is a subroutine that computes the product of 2 double-precision general matrices, hence the letter D in the subroutine name. These subroutines compute a scalar matrix-matrix product and add the result to a scalar matrix product with general matrices. We will set the values of alpha equal to 1 and beta equal to 0. As we scroll down the page, we can find explanations for the inputs to these subroutines. In our case, matrices ABC are n by n, so we will set mnk to be equal to n. The character trans A specifies the form of matrix A used in the matrix multiplication. In our case, we use the character n to indicate that matrix A is not transformed. The character trans B specifies the form of matrix B used in the matrix multiplication. In our case, we use the character n to indicate that matrix B is not transformed. Note that it is purely coincidental that the character n is the same letter as the integer n used for the matrix dimension. Once I signed into Fram, I observed that I was directed to the Login 1 node. Let's use the cd command to move to the MKL on Fram directory that I have created within my work folder. We can list the contents of this directory by executing the ll command. Let's take a look at a Fortran program that employs one Math Kernel Library routine for performing matrix multiplication. We observe that it utilizes a matrix size of 32, 7, 68. The MKL routine uses two variables, alpha and beta, as described in the documentation. The matrices are set up with values via an initialization loop, where the OpenMP directive is visible. Note that setting the C matrix to 0 is not needed when using the MKL routine. We set the variables alpha equal to 1 and beta equal to 0 because we are performing a simple matrix multiplication. The MKL routine DGEMM is called with inputs as specified in the documentation. The first two string variables, both containing the letter n, indicate that no operations should be performed on matrices A and B. The variable n represents the dimension of the matrices. It is coincidental that the variable name n for the matrix dimension matches the letter n in the first two string variables. We've named the job script to correspond with the Fortran program, distinguishing them by using an sh extension for the script and an F90 extension for the Fortran program. This naming convention indicates that the job script is intended to execute the Fortran program. However, this is just a suggestion, and you are free to use any naming convention you like. Let's review this job script using the Emacs editor. The job script starts by specifying names for the job and the slurm output file. Next, we define the computational resources needed for the job. We request a single node with a single task, since the Fortran program employs a pure multi-threading approach with shared memory for parallel computing, using OpenMP. The Fram Linux cluster provides 32 CPU cores per node, and we request to utilize all cores for our single task. We set the wall time to 30 minutes, enabling us to wait in the development queue. A production job would typically require a much longer wall time, necessitating a wait in the normal queue. In this situation, we must remove the Quality of Service (QoS) option. Regardless of the queue, we must specify the account number. The script variable file holds the name for both the script and the Fortran program, and this variable is utilized later in the script. The advised error handling environment is used. We also need to load the Intel Fortran compiler. Note that we are not using the alias Intel defined in the bash rc file. This is because we don't want our job script to depend on any specific configurations from the bash rc file in the home directory. The Fortran program uses OpenMP for parallel computing, so we are setting some OpenMP variables. The number of threads is set to match the number of CPU cores per task by using a slurm variable that retrieves this number from the computational resources specified in the script. Additionally, we are applying the OpenMP affinity settings cause and close. The script compiles the Fortran program to ensure it is built on the same type of compute nodes where it will execute. The highly optimized mapmul routine provided by the Intel compiler is replaced with the MKL routine. Therefore, we use specific compilation options to link the program with the Math Kernel Library. Note that the backslash simply indicates a continuation of the line. The complete option for linking MKL is shown in the video with red letters. We use the Intel compiler and the script variable file, which contains the name of the Fortran program. The resulting executable from the compilation process is named mxm.exe. We've added script variables to calculate the compilation duration, and this time is logged in the slurm output file. This measurement is optional, so you can choose whether to include it in your script. The executable is launched on the computational resources specified for the job. The time taken for the parallel computing is recorded using similar script variables, and you can decide whether to include this in your script. The remainder of the job script is unchanged and was reviewed in video 29. We submit the job script to the slurm queue system using the sbatch command. We can track the job using the sq command. The job has the specified name and has been active for 11 seconds on the C64 node. Using the sq command one more time confirms that the job has completed. The job script generates a slurm output file, but let's first clear the terminal. We can verify this by using the ll command, which shows that the file ending with txt has been created. You can also see that copies of both the job script and the Fortran program have been created. You can save these files along with the slurm output file to document which versions of the Fortran program and job script were used when executing this job. Let's open this slurm file using the Emacs editor. Remember to use the tab key for autocomplete while typing these long file names. The file first indicates when the job started and on which node it was executed. We can see that the compilation time was about 25 seconds, and the execution time was approximately 69 seconds. In video 29, we noted that the execution time using the highly optimized matmul routine from the Intel compiler was around 66 seconds, making it faster than the MKL routine for matrix multiplication. However, the Math Kernel Library offers access to many other routines beyond matrix multiplication. The job was submitted from the work folder. The specified computational resources are listed, showing that a single node with a single task using 32 CPU cores was requested. The CPU billing section shows that the billing factor was 32, which matches the number of CPU cores on one node. It also indicates that 59 GB of memory are available on a single node. The job consumed 0.8 CPU hours from the project account. The file shows that the job waited 1 second in the queue. Although the requested wall time was 30 minutes, the job had a wall time of 1.6 minutes. The computation was a single task on 32 CPU cores, with a CPU utilization of about 72%. The exit status was 0, indicating the job was successful. The used CPU time was 36.2 CPU minutes, and the unused CPU time was 13.9 CPU minutes, resulting in a CPU efficiency of about 72%. The low CPU efficiency occurred because only one core was used during compilation, leaving the other 31 cores idle until the compiled program was executed. The memory usage is reported as 25 GB. We can verify the job efficiency with the cef command, which stands for slurm efficiency. The command shows that the CPU efficiency was about 72%, and the memory usage was approximately 25 GB. Therefore, the scef command confirms the same numbers as those in the slurm output file. In our next video, we will examine the efficiency of jobs on the Fram Linux cluster. I am looking forward to the next video, wishing you all happy computing in the meantime.